Hello, everyone. Thank you for joining the GeoScience and GeoEnergy webinar of 13th of August 2020 today. It's quite warm here. I hope you are also in a cool area or having good time watching this webinar. It's our pleasure, both Sebastian and myself, to host you this week again with another webinar. I hope you have had or will soon be on a pleasant vacation in this summer as well. Wherever you go, make sure to connect and enjoy being a member of this life science program with pleasure. We are pleased to announce our keynote speaker of this week is Professor Andrew Curtis from the University of Edinburgh in Scotland. Andrew is Professor of Mathematical Geoscience since 2011. During 2017 and until 19, he was guest professor also at ETH Zurich in Switzerland. Prior to joining the University of Edinburgh, he was a senior research scientist, then principal research scientist at Schlumberger Cambridge Research Center. Before that, he was global corporate business venturing champion at Schlumberger, the same company. Andrew did his BSc, Bachelor of Science in Mathematics from the University of Edinburgh, where he actually today works. And he finished his PhD, though, at the University of Oxford in geophysics. He spent at Utrecht University, also in the Netherlands, for 3 years as postdoctoral research fellow. So quite a dynamic career. Andrew was the head of the Institute of Earth and Planetary Science at the University of Edinburgh between 2011 to 13. He was the founder and director of Edinburgh Seismic Research, then the UK's largest academic centre of exploration geophysics research. He was invited visiting professor at the Université de Paris in France. He has been also co-founder and leader of Schlumberger Mathematics Technical Community and co-founder of UK Corporate Innovation and Venturing Society. He's such a leader in the field. We are really pleased, Andrew, to have you here today. His research interests include wave-field interferometry and imaging, geoscientific statistical experimental design, inverse theory, and expert elicitation theory and risk analysis, which combines geology, economics, psychology, and uncertainty analysis in interface and design problems. His many awards and achievements cannot be listed here. You all should agree with me. I hope this gives a brief introduction about him, and would like to ask you all, please visit his Google Scholar page and university website page to learn more about his research and impact in the science domain. It is our pleasure to host you, Andrew, this week in our GeoScience and GeoEnergy webinar. To the audience, please note his lecture will last for about 30 minutes, followed by questions like before. Please type in the chat room your questions, and Sebastian will chair the discussion session. And also, please note, I'm going to share my screen, and Andrew would guide me through his slides. Andrew, thanks once more. The stage is yours.
Thank you very much indeed for that tongue twister of an introduction. I appreciate that. So it's a great pleasure to speak to you today. Now, I must say, although it's me speaking, in fact, a lot of the results you're going to see, in fact, most of the results that you will see today are actually from the PhD thesis of Xin Zhang at the University of Edinburgh. So all credit to him. So I think while Hadi gets the slides up to full screen, great. So today, I'm going to talk about some new methods to perform seismic tomography. So the methods to image the Earth's subsurface structure using seismic data. And the class of methods are called variational inference. Next slide, please. So what variational inference does is essentially uses optimization to estimate probability distributions. And the particular probability distributions I'm after are those that describe the uncertainty that we have in the Earth models, and that's defined by the family of all of the plausible Earth models after we've considered our whatever data we have. So the talk today is just going to follow this kind of schema. So I'll start, in fact, more than half of the talk, I'll be talking about variational inference, because this is not a class of methods that are very familiar to geophysicists, at least not in the tomography area, and not for estimating uncertainty. So I'll introduce variational inference. I'll then talk about applying them to travel time tomography using synthetic and then an application to real data from the Grana field next. And then finally, if there's time, I'll talk about their application to full waveform inversion. All of the material in this talk is in these two papers on the right. I can come back to them at the end, but they are available. The top one it really describes all of the theory that I'm about to present. Thanks. So what we're after is the left-hand side of this equation. This is called the posterior probability distribution, P of M given D. That's how we write the posterior distribution. Now, if M are the parameters that describe our Earth model and D is the data, then this describes, for any particular set of parameters M, how probable or how likely they are to be true, given the data set that we have. And this equation here is Bayes' rule. It tells us that that distribution, or that probability, is a combination of three terms. Top left, in the fraction, we have what's called the likelihood, and that is essentially the data fit. How well does the model fit the data? Sorry, that's top left in the fraction. Top right is the prior distribution, P of M, and that doesn't depend on the data at all. It just tells us how much information we have about the parameters independently of the data. And on the bottom of the fraction, we have what's called the evidence, P of D. Now, the important thing about that term is it's computationally intractable for most practical problems. We cannot calculate it, and I'm going to come back to that within a slide or so's time. Next. So normally when we try to characterize this probability distribution, and this distribution, that is what describes our uncertainty about the Earth models. It tells us which models are more or less likely given the data. And normally what we have to do is stochastic or random sampling. So we have to, we take samples, so many different sets of model parameters M. And for each one, we calculate the probability distribution, and we select the parameters in such a way that we get samples which reflect their relative probability. So that gives us a sort of characterization of this, the topography of this probability or uncertainty. The problem is that random sampling methods are very inefficient, and we'll see that, an example of this in a moment. And so what we would like to do is to replace those with optimization, because optimization are a very well understood class of methods. We also understand their convergence properties, and that's something which we don't understand well for stochastic or random sampling methods. So if we can convert these problems to optimization, we may well do them more efficiently and have a better idea of the solutions, the quality of the solutions. So we're going to look at this converting to optimization using two different strategies. And the first is we're going to fit semi-analytic functions to this probability distribution. So next, so what we'll try to do, the way that we'll do this is we'll first choose a family of functions, and the function, let's call them Q. So each of these will be probability distributions. So for example, they could be Gaussians, defined by their mean and covariance matrix. And then within that family, next, we will try to optimize the parameters of the distribution, so the mean and the covariance, such that we find the Q that best fits P, our posterior. So within that family, we'll try to find the single distribution which is the best fit to what we want. So next, graphically, the way that that looks is we have, this is just one parameter case, one model parameter on the horizontal axis, probability going upwards. So we have a posterior distribution that we don't know. We don't know the form of it, but it's there. Next. And we take some initial estimate from this family of distributions Q. And it's, let's say, Gaussian next, which is characterized by its mean next and its covariance. And then what we want to do is to work out how should we change those parameters to better fit the posterior distribution. So we might find, yes, that the first parameter, the mean, has to move to the right, and we might want to decrease the covariance next. And so when we do that, we get closer to the posterior. And then we do it again, next, and next, and next, and next. And then, so thereby, we've gone through an iterative process to get a best fit to the solution. So overall, in order to effect that strategy, we have to define some measure of the difference between Q and P, and then we have to minimize it. And when we have, that is an optimization. And so when we've reached the optimal function, we just still don't know P, but we do know Q. And as you can see, hopefully we've got a reasonable approximation to P. So yeah, next. So then we'll try a separate strategy next. And this strategy is quite different. It is, instead of trying to fit a function to P, we will generate a set of samples of P, but not by random sampling, by optimization. Now that sounds quite different from strategy one, except that the samples next are actually distributed implicitly by a distribution Q. Again, now we're not making an explicit function like Gaussian here for Q. We don't have to define one. We're actually going to use the samples themselves to define Q, and then we'll optimize the samples. So the way this will work graphically is we might start with our prior distribution there, P of M, and next we take a set of samples of the prior distribution. You can see just a set of random samples. And then next, we work out which way we would now perturb the samples to better fit P next. And we see it's in this direction. So next, we perturb them and again, until there we are, we have a set of samples. Now, the interesting thing about this method of strategy is it produces samples, but these are clearly not random samples. These samples are optimally distributed to represent P, in the sense that, if you click next, their sampling distribution Q, which is implicit, is a best approximation to P. And so it turns out next that in both of these strategies, actually what we have to do is to define some measure of the difference between Q and P and then minimize it, whether we're trying to find an explicit Q or a set of samples. So what is this measure of difference next? So we're going to use a fairly standard measure. It's called the Coolback-Leibler divergence, and it just measures the difference between two probability distributions. So we denote it KL, Q to P on the left there. And it's given by this expression, which is a little bit complicated looking. We'll come back to it in a minute, but just note that in the first term on the right, we have Q in the middle of it. In the second term, we have P. So, and there's a difference between them. So that's measuring the difference between the distributions. The nice thing about this measure next is that KL divergence is always greater than or equal to 0, and it only equals 0 if Q equals P. So we can try to find Q by minimizing the KL divergence. Try to find the Q, sorry, the best equals P by minimizing the KL divergence. Next. So on the right-hand side, we have a problem because that log P of D, remember, P of D is the evidence that was on the denominator in Bayes' rule. And that was the one I said was computationally intractable. So it looks from the face of it as though we have a problem because we can't calculate the KL divergence. But we can get around this next by rearranging the equation to put the other terms on the right in that equation onto the left, and that's what you see here. So now we've only got the evidence on the right, and we have these three terms on the left. Now next, the other thing about the evidence is that it's constant with respect to Q. So if we're going to use the KL divergence to find the best fitting Q, we're going to change Q. The right-hand side is going to be absolutely constant. We don't know what the constant is, but it will not change. So what that means is, next, if we want to minimize the KL divergence, we can equivalently, next, maximize the total of these two terms. And these two terms are so important, next, that we give them a name. It's called the evidence lower bound, or the elbow. And the reason we give them that name is because the KL divergence on the left of that equation, the underlined KL divergence, is always positive or zero. So that means that the elbow, the other two terms, are always less than the log evidence. So they are a lower bound on the evidence, and they only equal the evidence if our approximation Q is a perfect match to P. So what we can do then is maximize the elbow. And next, that will be our strategy here. We will maximize the elbow, and that will automatically minimize the KL divergence, or the difference between Q and P. And so it will give the best approximation Q to the probability distribution P that we don't know, and that is what we're after. Next. So if we have a look a little bit closer at the mathematics there, we can see first that the, sorry, can we go back one? So these two terms here are, we can see the notation is capital E, Q of M, and then we have square brackets with the log P or the log Q in it, in both of these two terms. Now, this capital E means expectation or average value. And it's the average value of what is in the square brackets, so say log of P for the first term, but for values of M distributed according to Q of M. So in other words, if we were to calculate this, say the first term, so 2, we could take samples M from Q of M and plug them in, each one into the brackets to calculate what the value is of log P of M, given D, and take the average value of those values. And that is the expectation of what's inside the bracket. So that's how we calculate these terms. Now, the nice thing about this is that the samples are taken with respect to Q. And remember, we choose Q. We choose its family of Qs, the family of Qs that we might consider. So we can choose Qs that are easy to sample from. Next. The other thing is that within that square bracket is our posterior distribution. So that's what we're ultimately after. And so Bayes' rule, the prior, the likelihood, everything is in there. Now it turns out that if this has this model parameterization and the data have particular types of structures, for example, if our model is gridded, spatial model on a gridded basis, as most of our models are, many of them are. If our data is localized in some way, for example, let's say we have a 3D seismic cube where we have an image in 3D, and each value or each pixel of that image relates to the structure localized somewhere around that pixel. So it's related to the petrophysical properties, the lithologies, the fluid content, and so on, close to that pixel, not necessarily at it, because there's always blurring and errors in the image, but local to it. In these cases, even if we have very sophisticated, complex statistical prior geological information, next, we can derive solutions to this optimization problem almost analytically. And that makes solving these problems using variational methods incredibly efficient. So that 3D seismic one, for example, that I just described, could be solved on a laptop computer, even with very sophisticated multi-point statistical geological information. And that isn't really possible, or at least not in any reasonable time, using sampling methods. Now, if you're interested in that kind of application, oh, sorry, go back. In that kind of no, sorry, stay there. Thank you. So, if you're interested in that kind of application, have a look at the papers by Atif Nawaz from his thesis. Got 3 papers there, which are specifically on those kind of localized problems. Now, the problem with them, though, is that they are case specific. So they are specific to different kinds of model data relationships, and really that's the key. In this talk, I'm going to focus instead on methods that are quite general. We don't make assumptions about the form of the model parameters in the data. So, so they're applicable to almost any of our natural optimization or inference problems that we encounter. Next. So we're going to now have a look at 2 methods which follow these 2 strategies that I mentioned. And the first one is called automatic differential variational inference. We're going to call this ADVI from now on. Next. So ADVI is that special simplest case that I actually mentioned on slide 2, where we would like to fit a Gaussian, the best fit Gaussian, roughly speaking, to our posterior distribution. And that sounds like a simple problem. And it almost is, with a few subtleties. But let's just go through this method to understand how these variational methods work. So the first thing we have to be careful of is that Gaussians are defined on the whole space of real numbers, positive and negative, always from -infinity to infinity, whereas our normal physical parameters are usually constrained. Seismic velocities are greater than 0, porosities between 0 and 1, and so on. So the first thing we need is a transform T, which will take our physical parameters to an unconstrained space of real numbers. After we've done that and transformed the problem, next, we will assume that the family of functions we're considering are the Gaussians, so the normal distributions, and they will be denoted by normal distributions theta, which is our unbounded variables, and the normal distributions are defined by their mean mu and covariance L squared. Now, what we next do is we use a standard transform to transform that normal distribution to what's called a standard normal distribution. So that's a normal distribution with mean 0 and variance 1. So 0 and the identity matrix I are the mean and the covariances in this case. And the reason that we transform to a standard case is that in that case, we can work out next the values of the gradient of the elbow with respect to our parameters, the mean and the covariances. Now, these equations look complicated. Again, don't worry about that just yet. On the left of them, the left-hand side is grad of this curly L is what we're using for the elbow. So it's the gradient of the elbow with respect to mu. So if we change mu, the mean, how do we change the elbow? And if we change L on the second equation, how does that change the elbow? And knowing those gradients allows us to maximize the elbow next. We can simply use any gradient ascent algorithm to maximize the elbow, which, remember, minimizes the difference between Q and P automatically. So it's the calculation of these gradients which is the key in these variational methods. Now, if we have a look at the right-hand side of these equations, they look complicated. However, all of the terms on the right-hand side, so everything from log det onwards in both equations, that is all completely analytic. So there is nothing to do there numerically at all. The other terms inside the square brackets are grad of m log p, okay, in both equations. That is the gradient of the, in fact, the joint distribution between data and models with respect to our model parameters. Those are almost exactly, or they are transformed versions of exactly the same derivatives as we always use when we do linearized inversion of the data for for the model parameters. In other words, if you can calculate the gradients of your data with respect to the model parameters to do linearized inversion, then you can just convert that very easily to get this ADVI estimate of the non-linearized best fit Gaussian to non-linearized, I should say, posterior distribution, just by plugging them in. Next. The other thing is that these expectations now are really easy to calculate because they are expectations with respect to this standard normal distribution, N01. And because we're going to perturb we're going to iterate these formulae over and over again, perturbing our distribution Q. We actually need to take very few samples. Even one sample is enough for some problems because we will iterate these formulae many times. And typically we will use about 10 samples per iteration, of the order of 10 for what you'll see today. So this is nothing like taking a set of samples for Monte Carlo and the posterior. It's not even on the same scale. So that's ADVI. So the only thing that we haven't defined yet is this at the top, the transform T, to go from bounded to unbounded space. Next. So the one that we use is just this simple log transform for variables that are bounded between A and B. This transform takes them to an unbounded space. And below you can see an example in orange of a bounded PDF, which gets transformed to an unbounded PDF in blue. And that's all we need. So next, this just shows an example of it actually working. So top left, we have in red the posterior PDF, and we don't know it. So it's bounded from 0 to 5. So we use our transform to move to an unbounded space in the middle top diagram. And there we take an initial estimate, Q, which is the blue curve, initial estimate of the posterior. The transform posterior is now shown in red. We then transform this space to the standard Gaussian using the standard transform to get to a standard normal distribution on the right, and that's got mean 0, variance 1. And then moving to the bottom row, we optimize in an iterative, using those formulae iteratively, we optimize the mean and the standard deviation to best fit posterior. And then finally, bottom left, we transform back to the original set of variables, and we get a very good approximation to the posterior. So that is ADVI, and that is the first method. Now, clearly, this whole method, the shape of that final distribution depends on the transform, and we chose that to be that logarithmic form, but we could have chosen a different transform. So we're now going to move on to the second strategy, which is a bit different. Next slide. And in this strategy, we're going to start with an initial distribution Q0, and then we're going to design a sequence of transforms, T0, T1, etc. up to Tn. And they are going to transform our initial distribution Q0 up to a final distribution Qn, which we would like to approximate the posterior P. So next, so the strategy here is to optimize the transforms by minimizing the KL divergence between Qn and P. And this next leads to a set of methods, most notably either normalizing flows or Stein variational methods. Now, I'm going to leave flows today, so we don't have time for those. We're going to talk about Stein variational methods. Next slide. So in Stein methods, we assume a form for the transformation. Now, these transforms have to be invertible for the methods to work. And so we assume a transform of the form shown here, that any model will be transformed to the model plus a small perturbation, epsilon, in direction phi. And phi depends on the model parameters. So each particular point in parameter space will be deformed, if you like, a little bit in a direction phi that may be different for different parts of parameter space. And it's only going to be a small deformation because we're going to keep epsilon small. And the reason we keep it small is that that makes T almost exactly invertible. So what we need to know here is which direction to deform to give our optimal transforms so that we can approximate the posterior. And we can work this out analytically, and that was shown by Liu and Wang. Next. So they showed that the gradient of the KL divergence on the left with respect to a step in direction phi of length epsilon is given by all that expression on the right. Again, let's not worry about the complexity of the maths just yet. The point is that they have an analytical expression there for how the KL divergence is going to change if we take a step. Now, so if you go next, this means that for any particular point, we need to know which direction to go in, and the best direction that we can go in is going to be the one that maximizes the gradient that is given in this expression. And again, what Liu and Wang showed was that we can actually find the maximum of this expression with respect to phi, the direction, next, and it's given by this set of equations. Again, don't worry about the maths just yet. It's just another expression which actually uses similar terms to those we saw before. So phi star here is given analytically by that equation second from bottom. And that phi star is, next, it is the direction which has the largest change in the KL divergence. In other words, it's the direction that gives us the best step towards fitting the posterior distribution. Now, next, if we look at the maths, then we again see this gradient of log of p. This is now the gradient of the posterior with respect to m. Again, this is exactly the same, or formed from exactly the same gradients as we use in linearized inversion. So if you have a code that does linearized inversion, you can convert it to do Stein variational gradient descent very easily by just plugging these formulae in. Next, the other part of this is again the expectation. And again, we're going to do this by taking samples. And these samples, you'll note, are distributed according to Q, but we haven't defined Q. And that is because Q in this method is simply defined to be the sampling distribution that we use. So we can start with any distribution of samples Q, for example. Again, we could start with our prior distribution and take that set of samples. We plug them into the bottom equations to find the best directions phi to move those samples. And then we use the transform at the top, T of m. We just perturb those samples to new positions, which is m plus a small step epsilon in this optimal direction, phi star. Those new samples we then use for the next iteration to calculate the bottom equation and perturb again. And we just iterate over and over and over, moving our samples according to this transform. Now, what that shows you is that although these samples are distributed according to Q, their sampling distribution, we never actually know it explicitly. It is simply how the samples are distributed. Yet, by doing this, we've shown analytically on this slide that we minimize the KL divergence. In other words, that sampling distribution converges towards P, our posterior distribution. So that is what we're going to do. So next, so this shows the Stein variational method, SVGD, working. So at the top, we have the posterior, it's now in blue, we don't know what it is, but we know we construct a set of samples, in this case, say 500 samples, and the histogram of those samples from our prior, say, is shown by the pink histogram. We then use those samples and iterate them through the equations on the previous slide 5 times, and we get the middle histogram. And already we're starting to see a reasonable approximation to the posterior. After 500 iterations, we get to the bottom, we have a near perfect representation of the posterior. Now, although we are generating samples here, this is really very different from random sampling. And to make that clear, if we go to the next slide, we have a representation here, it's just a demo app, of a random sampler. So this is what the kind of method that would typically be used. So in the contours there, in the shading, we have some posterior distribution we don't know. And the Metropolis Hastings Monte Carlo method, a very popular one, is a random walker. It's random walking, but every time it takes a step, it has to evaluate the forward function at least once. Whenever it tries to take a step and you get a red arrow, it rejects that sample for reasons that are required in the probability theory. And it takes another sample and another sample until it finds one that it accepts. That means it's wasting a lot of compute time. And for this reason, these Monte Carlo methods are really quite inefficient. Well, not necessarily inefficient, because they provide exactly a random sample eventually of the samples of the posterior, but they are slow to convert, let's put it that way. On the other hand, SVGD, if you go to the next slide, takes a very different approach. So we start with a random distribution of samples, as you can see here. So it's just from a Gaussian. At each sample, we calculate the phi, which is the optimal direction to deform the sample space. And then click, next slide, we see them self-organizing iteratively to optimally represent the posterior with their sampling distribution. So while it's true that SVGD is giving us a set of samples, these are not random samples. They are actually optimal samples, such that their sampling distribution optimally reflects posterior. So that's the difference between them. Okay, next. So let's have a look at some synthetic tests. So here's an example. This is a simple tomographic example. We have, let's call this the true synthetic Earth. So it's a synthetic example of the true Earth, let's say. So we have a velocity structure, which is constant. It's 2 kilometers per second in blue, with a low velocity, 1 kilometer per second anomaly in the middle, a circular one. And that's what we would like to image. And we'd like to do it with travel times measured between each of the locations of these triangles. So we can imagine these triangles are receivers, and typically in seismology these days, we might measure travel times by using ambient noise interferometry. So we measure ambient noise, we cross-correlate it, and we use some now fairly standard processing methods to measure the travel times of waves between every pair of those triangles. And that's the data set that we have. And just using the travel times of waves between them, we'd like to image the medium. That is travel time tomography. Next. So first of all, let's have a look at a solution with the only Monte Carlo method that is efficient enough to, roughly speaking, converge. Now, it isn't actually converged, but it's at least converged in terms of the means and perhaps the standard deviation. And this is a very particular method. It's called a reversible jump Markov chain Monte Carlo, which uses a very sophisticated varying parameterization. So it's not parameterizing in the same way as we might usually think. I'll show you that in a minute. But next, let's have a look at the solution first. So the mean image that this method gets is shown in the middle, and it's quite a reasonable representation of the truth. And the standard deviation on the right. If you look at the standard deviation, well, the mean, as I say, is quite a good representation of the true model in this case. The standard deviation on the right has very low uncertainties in dark blue. It's got high uncertainties in the middle, and then the highest uncertainties inside the receiver array are a sort of loop around the low velocity anomaly, marking its edge. And that's because our largest uncertainty, in fact, is in where exactly the edge of the anomaly lies. So that is what this uncertainty loop is reflecting. Now, although this looks like a great solution, it's not actually the uncertainty in an image as we might normally think of it. We normally think of an image as like a photo. So it's a pixelated image on a regular grid. And we want to know what is the best model under that parameterization and what's its uncertainty. But that's not what this method gives us. If you click next, in fact, this method is using a highly variable parameterization. Every sample uses a different parameterization, which are parameterized by Voronoi cells, in this case, which can be very large and within which they always have constant velocity. That's how we set up this particular problem. Now, this makes the Monte Carlo method more tractable, because with larger cells, that means it has many fewer cells, fewer parameters, and hence it becomes more rapid to reach some sort of convergence in the sampling. However, this is not giving us the uncertainty in an image as we would normally think of it. It's actually, this mean that we're getting is actually the mean at each point of all those models, or similar models to the ones on the left. And none of those models look like an image of geology. So we have to be very careful in the way we interpret this. In fact, the uncertainty here is actually very difficult to interpret. So, nevertheless, this is the only method we have that is really converging for this, well, roughly converging. And so let's now look at what the two variational methods give us next. So the first is ADVI. Now this is parameterized on a regular grid, just like a photo, kind of thing you'd normally imagine as an image. The mean is giving us a nice circular low velocity anomaly, but it's not got the same velocity as the true model. That's absolutely fine, because remember, this is the mean, on the right, the standard deviation of the family of all models which are plausible given the data. And we have no idea what that mean should be. And it's certainly no reason why it should equal the true model, and it doesn't. Okay. So we have that low velocity zone, and around it we can see this sort of faint halo of another low velocity region, like a donut around the middle, within the blue, within the dark blue. On the right, we see standard deviations. There is also a very faint halo around in the dark blue area. And in the central high uncertainty bit, if you look very closely, there's also an uncertainty loop there, but a very diffuse one. So the center is very slightly more certain than the edges. So some hint of these loops that we just saw, but certainly not the same. Now, we don't know whether this solution is correct or not. So let's try another method next. This is the result from SVGD. Now, if you just go back to ADVI and forward again, and compare the means, you see the mean is almost identical, okay, between the two. On the other hand, the standard deviation is quite different. So for SVGD, in the standard deviation, we can see two distinct halos. They're quite diffuse, but they're definitely distinct halos around within that sort of otherwise dark blue area. So now, where we've come to is we have compared three methods, one Monte Carlo one and two variational methods, and all three are giving different solutions. So, which one is correct? Well, the only way to find out is to try a fourth method. So we tried a Monte Carlo method on a regular gridded cell. Now, there is no way to get this to converge. It is, even with only 21 by 21 cells, 400 parameters, if you just do, as we did here on the next slide, a Metropolis Hastings Monte Carlo, it certainly has not converged, but it was converging. We could see that. And so we took samples from it anyway and used those to calculate the mean and standard deviation. And again, we see the mean is identical almost to the previous ones. What's more, the standard deviation, if you step back and forward a couple of times, Hadi, those two. Then we see that they both contain the same double halo. So they're not identical values, but they contain the same halo. So it seems that SVGD has found probably the right solution. So two of these methods, certainly Metropolis Hastings, should not be a biased method. Excuse me. So the fact that both it and SVGD are seeing this roughly the same structure means that that's probably the correct solution to our imaging problem. So, excuse me, just a moment, I'll just have a drink. Okay. So, we think this is the solution. Next, it is not the solution found in the next slide by the reversible jump method. And so what this shows is, next, because of this variable parameterization, we have to be very careful how we interpret these reversible jump methods. They are clearly valuable because they actually converge, and they converge to something that looks informative. But how to interpret those uncertainties is really not obvious. And in particular, they certainly don't represent the uncertainty on a regular gridded image. That has been shown by the past few slides. Now, if we go to the next slide, this is the solution that we think is approximately right. And in fact, this has led us to think that SVGD is a good trade-off between the other methods. If we go to the next slide, this is because if we look at the computation in the second column, so the two variational methods at the top, the two Monte Carlo methods at the bottom, we can see that there is a hugely reduced amount of computation in the variational methods. ADVI uses 10,000 samples. Both Monte Carlo methods use millions of samples, and the Metropolis Hastings one at 12 million still hasn't converged. ADVI, on the other hand, did not give a good representation of the uncertainties, but SVGD did, and it's still a really significant reduction factor of 10 on the best Monte Carlo method, and it's giving us uncertainty on a gridded image rather than this reduced transdimensional parameterization. So SVGD, we think, gives a really good trade-off. Next. So let's see an example on real data, just very quickly. This is a field. These are receivers on the seabed in the North Sea, and we just did the same thing. We used ambient noise to find travel times between, in this case, the red receivers and all the blue ones, and we used them to do tomography. So the scale of this is about 5 kilometers across and 13 kilometers north-south. Next, we find this solution from ADVI, quite a complex mean structure there, and standard deviations on the right. And then compare that to next slide, SVGD, we see the mean on the next has not changed much at all. If we compare those two slides, we see that the mean is almost the same. So we're pretty confident of that. Now, ADVI, we don't expect to give the right uncertainties. SVGD, we do. And so we think that the uncertainties in SVGD are probably more likely to be correct. Now, we could not run Metropolis Hastings on this. It was just intractable. We could run the variable dimensionality or transdimensional method, if we see that next. And we see, again, the uncertainties now are quite different, but we expect that. It's solving a different problem. The mean structure, if we compare to the previous slide, is on a large scale really very similar. It's seeing the same Earth. There's no question about that. But remember, the mean structure from the two variational methods, two different methods, agrees very well. And they're certainly much more detailed than this. Even though the Monte Carlo here has run for 13 million samples, whereas on the previous slide, SVGD only had 500,000, so 500,000, and ADVI only had 10,000. So again, we think in this case that SVGD is giving really much more detailed information than the Monte Carlo at far, far fewer samples. Next slide. So, Hadi, I can see the time. I can stop now or spend 5 minutes. It's completely up to you. Is anybody there?
So I would suggest just spend 5 minutes to finish up your, I'm just speaking on behalf of Hadi here, just finish.
Okay,
5 minutes, Andrew?
Yeah, 5 minutes would be fine. I had muted myself to cause no disturbances. So please, yeah, 5 minutes should be fine. Okay, great. Thank you very much. Okay, so let's now see exactly the same methods applied to FWI. Now we're actually going to just apply SVGD now. We're not going to bother about the other methods. Next slide. So in full waveform inversion, what we want to do is find out about Earth structure from a set of waveforms that we record at receivers, say the triangles, by firing sources that
our waves into the subsurface, they reverberate, and we record seismograms as shown in the bottom plot here. Now the forward function in this case consists of firing the source in whatever synthetic model we're using and letting the waves reverberate and recording them. And that is extremely expensive. So for any recorded data, we need to solve the inverse problem as efficiently as we can. And so that's what's important here. Yet, we don't just want to estimate best fitting models, because we know there are infinitely many of them. We want to constrain the family of all of the models that are consistent with the data. So we want to get the uncertainty. Next slide. So this shows the model that we're going to use for our test case. It's a very simple model. It's got just this sort of peaked structure overlain by regularly horizontal sediments, sedimentary layers. And we're going to, it's a fully elastic model next. It's got VP on the top, VS in the middle, density on the bottom. We've got 7 sources which are at the bottom of the model, and these are double couple sources like earthquake sources, recorded at 19 receivers on the top of the model. So this is a transmission case. The receivers are two-dimensional, two-component. So on the right, we can see a vertical and a horizontal example of the waveforms. And we're going to invert for the structure within the dashed rectangular box inside the image there. And we'll parameterize it with a regular grid of 180 times 60 parameters, and that's 3 parameters per cell, so that gives us a total of about 30,000 parameters. For prior information, we're going to use uniform distributions, which are really very tight. So you can see them listed on the bottom left there. And next, the reason that we use this model and those type priors is identical to the problem solved by Lars Gebrad in a study published last year. And he solved, or tried to solve this problem using Hamiltonian Monte Carlo. So he tried to find the family of posterior models which are consistent with the data for this problem. And so we try to do the same here using SVGD, because then we can compare to his results and hopefully validate both methods. Next. So the data is shown here. This is the full set of data. Each of the sources is concatenated in the horizontal direction. You can see the 19 receivers vertically. We use a least squares misfit function on the right and a likelihood function that's shown by e to the -5 there on the right. I'm not going to go into the details of this. You can see them in this paper if you're interested. Next. So we're going to use SVGD next, which, as you know, is going to flow samples to represent the posterior, and it's going to give us an optimal set of samples to represent that. Next. And we're going to compare this to Hamiltonian Monte Carlo. Now, this is similar to the previous one, except it's a smarter method. It's much more efficient for many problems, because what you'll see here is it's getting many more green arrows, many more acceptances, by doing smart path-based way of proposing models. So that is what Lars used, and we used SVGD. Next. So here's the true model. Next. Put that to one side, and now let's see the results next. So SVGD gets these results. If we just look at the top row first, that's VP, and we can see that the mean estimate is very poor. We don't resolve VP well at all, and on the right, we've got very high standard deviations. On the second row, we see VS. We see we get a pretty good representation of VS mean structure, and the uncertainties reflect that same geometry. And on the bottom, the density, we can see the structure, but the values aren't really very correct as far as the mean is concerned. Anyway, they don't represent the reality, but neither should they. Now let's compare that to the results that Lars got on the next slide, and we see they've really changed very little. In other words, comparing these two slides, we see almost the same structure, and we see the same family of structures and the same uncertainties. And this really validates both of the methods, because Lars didn't know whether he'd found the right solution. Neither would we if we hadn't got his. So now both of the methods, we can be fairly sure they're converging to the right thing. Next. Even if we look in detail, and I can't unfortunately point with my mouse, but if you look in detail, for example, On the bottom, slightly to the left of center, you can see some lines in the red, diagonal lines on the in the red area of the model, of the image. They appear on both of these solutions. Now, if we'd only seen them in one, we would think it could well be an error of the method, but these are completely different methods, and we both see them. So these are true. They are part of the mean of the family of models that fit the data. Next. What's interesting about this is that the Monte Carlo mean here is taken from 10,000 samples, which are randomly distributed, whereas the SVGD mean you're seeing is from only the 600 samples that we took originally, and then perturbed, we flowed them to get the final estimate. And next, that's because these 600 samples are optimally distributed. And you can see that we also see very similar standard deviation structures, including all of the details as well. Next. So the optimality of those 600 samples means that this might help also with storage. If we have large 3D or even 4D models, and we want to take many, many samples and store them, clearly we would prefer to store optimally distributed samples than simply random samples. So we think also SVGD could well help with that. Next. So in summary then, we've introduced these two variational methods and compared them to two, in fact, in 3 different Monte Carlo methods. SVGD certainly seems to be a reasonable trade-off between computation and finding good uncertainty estimates. And I would just encourage you to try these methods. If you can do linearized inversion, you can do either of these methods very easily by converting your codes, or at least certainly from a theoretical point of view. Depends how complex your codes are, but if you can calculate gradients, you can use these methods. So I'm sure these are going to have a significant impact in the future in geophysics, and I would just encourage you, particularly all you PhD students out there or master's students, have a go with them. See if they solve your problems, and if you're interested, just look at those papers down the bottom. They're on my web pages. I must say that my web pages right now are in flux. They exist, but I'm not sure quite what's going to happen to them. So if you have any problems, just email me directly. Thank you very much for your attention.
Thank you very much, Andrew, for this very nice presentation. I'm trying to bring myself back if I find the way I can operate this gadget. And you yourself could also please try to be back and see if the network would be well. Thanks a lot. I mean, that was quite a comprehensive study of the work and the questions. Already I have seen that they are posted. I would like to give the floor to Sebastian, and if time allows, I would preserve a little bit of time for myself also to pose a little bit of question, but Sebastian is the boss, so he will decide. Okay.
Well, thank you very much, Andrew, and thank you to the audience for questions. Just quick explanation for those of you who don't know, Andrew and I were both in Edinburgh, and we had some absolutely horrendous rain the night before, and yesterday there were 100,000 homes without internet in Edinburgh, and so things are just coming slowly back online here.
That's why I had Hadi controlling the slides for me, which I was very grateful for, Hadi. You did a great job.
Oh, thank you very much. I was quite nervous to see that when...
So, Hadi, considering that, and we do have some questions, I'm not going to take away anything from the audience, but as a little thank you for managing the talk, why don't you start with your question first?
Well, thanks very much, Sebastian, and I'm really impressed to see how severe that rain and storm was there. So to start off with this very nice and important study, we stand in the reservoir simulation or reservoir modeling, and the geophysics and inversion to understand and characterize the reservoir stands as the core of the business, because when you cannot see it, how can you model and predict the dynamic feature of it? And now it comes to combine the two fields to see that the reservoir has some dynamics feature, and you've got the transport properties, pressure change, and so your wave properties and the measurements might get impacted by the dynamics that happens in the reservoir. Would these methods be sensitive in inversion when the process is time dependent and changes?
So sensitivity would be really nothing to do with these methods in particular. They would just be defined by your, let's say, your derivatives of your data with respect to whatever parameters it is you're interested in, the flow parameters, the dynamic parameters. Now, usually we can use a variety of methods and simulation packages to calculate these derivatives. I mean, they're used a lot, as you know, I'm sure. So those derivatives are available. These methods would give you a nice framework to put them into, to try to use the derivatives to get uncertainty estimates, but not linearized uncertainty estimates. That's the important thing to stress about this. Although we're using derivatives and they are normally associated with linearized methods, in fact, in these methods, we use the derivatives to get fully nonlinear estimates of uncertainty. So yes, I think they would be useful. It's not to do with the sensitivity, but certainly to estimate uncertainties on your dynamic parameters.
I see. And one other question I had was about that. That's a pretty much clear answer. Thanks a lot. It's very much helpful now for me to understand the whole picture. The measurements can be multi-resolutional as well, and from multi sources. So you've got the data, but they may be in different spaces. Like if you combine electromagnetics, which might be a little bit, or near well measurements combined with the global data sets, that might be in different space, like seismic as well. How would be the best to deal with this multi-resolution data to find the better way that maybe you have some local zones that you would like to understand, or have a little bit of more confidence zone, because that's where the leakage might happen?
Right. So the first thing with different data sets or different data types is the only way that you can rigorously combine these or formally combine these is by having data uncertainties. So if you have uncertainties on your data and you know these derivatives, let's say, within this formulation, then automatically the Bayesian solution will adjust for the information content of the different data sets. Now, the problem comes usually because it's very difficult to define the uncertainties in your data. If you have a seismogram, it's very difficult to define that. The way that we deal with that, if we have enough compute power, is to set up a hierarchical system where we actually invert for the data uncertainties as well. So they become parameters of the model. And so we've done that a lot with Monte Carlo methods, particularly this reversible trump or transdimensional one that you saw. It does, of course, increase the number of parameters. It makes it more difficult to assess the uncertainties in the data. Nevertheless, we've actually just published recently a version of these variational methods which works hierarchically, which also gives you an estimate of data uncertainties. So my feeling is that formally you can do it, and these Bayesian solutions automatically adjust for the information content in the data. Computationally is another thing, and I think future studies are just going to have to work out what is tractable and what is not.
I see. So if Sebastian allows me, I would like to connect my question to one of the posted questions here. And Sebastian, you should somehow give me a signal that I should stop. But there was a question here posted about computational extensive, or the cost of the computation on the and bringing the things into the parallel processing, and so that if they are amenable for parallel processing and distributed memory type of this analysis for larger scale problems. Do you have any comments about those type of implementation of these methods in the new architecture and multi-core systems and so?
Just specifically, sorry for interrupting, Stanley Wang asks, thanks you for the talk, and asks, is it possible to use ADVI and SVGD for parallel?
Yeah, so I didn't mention this, but this is actually one of the major advantages of these methods. And this is what makes them really practical. So if you use random sampling methods, stochastic sampling Markov chains in particular, they are very difficult to parallelize other than just putting several different chains sort of in parallel. But within a chain, they're extremely difficult to parallelize because there's a mathematical property called detailed balance that has to hold from sample to sample through the chain. So you can't have parallel processors developing new samples because that will not preserve detailed balance. So actually, one of the major advantages of this is that we can now use optimization libraries which are fully parallelized, and the problems using SVGD and ADVI are fully parallelizable. So this, I think, is probably the main property which will allow us, for example, to extend these beyond the toy full waveform inversion problem I showed to something a lot more realistic. And that is what we're sort of working on right now, but I think it will be facilitated by this parallelization.
Thank you, Andrew. We have a question from Yan Zhang, again, thanking you for the talk. He says, I'm not familiar with the topic, but interested in understanding what main field variables are used for inverse problem for seismic tomography. What are the key field variables that you're solving for?
Yeah, so in the waveform inversion example there, I showed you them explicitly. So it was I called them the P velocity, the shear velocity, and the density. So essentially, I've got a gridded model in space, and in each of those cells, it's a set of cells regularly spaced. In each cell, I've got two velocities and one density. The density is just the density of the rock. The velocities are the speeds with which P waves or shear waves, so two different kinds of elastic waves, travel through that medium. So those are the main dependencies on the data. Now, those are not necessarily the variables that we want to know. We want to know things like what is the rock made of, what's the fluid content, is it volcanic, is it sedimentary, all sorts of questions like that. But the main dependency is on elastic properties or inelastic properties of the rocks. And so those are the main variables.
Thank you again. So we have a question from Mr. JVLJ. Don't know what the full name is. And you mentioned gridding, Andrew, and there's a follow-up question here. I was wondering if an irregular grid, especially the single-sided one, has an effect on the results compared to the very regular grid that were used in your synthetic examples.
Yes. So I'm not quite sure what you mean by single-sided grid, but let me say that so that's what I was trying to get across when I showed you the solution that we found in the travel time tomography. So the simple problem with a low velocity zone, we found that the travel time tomography solution that we found with both SVGD and with the Monte Carlo methods was they were calculated on a regular grid, and they were quite different from the one calculated on the irregular grid. Now, the reason for that is that that reversible jump method is actually not inverting for images at all. It's inverting for Earth models that consist of irregular gridded cells within which there is constant velocity. And that is a completely different inverse problem to solving for the velocities on a regular grid of cells. So it's no wonder we get a different solution, but I must admit, we've been using those methods for years, and it's not until we had these variational methods to compare to that we realized just quite how different the solutions are, and also quite how difficult they are to interpret, these solutions from the reversible jump methods, because now those uncertainties are over. Those are uncertainties over varying dimensions of parameter space, as well as varying in space and so on. It's really not obvious how to interpret them. So yes, the variable parameterization changes everything, in my view.
Thank you very much, Andrew. So well past our normal speaking time.
Sorry about that.
No problem, Andrew, not at all. Handing over to Hadi for some final comments.
Yeah. Thanks very much. And I'm receiving some text from friends that they are in the lab and are looking forward to watch the video after their operational service, where now they are allowed to be back in the lab. So good news.
Right.
So thanks a lot. And again, it was really a comprehensive and quite a very engaging also talk. I would like to just take the chance to announce that our next week's speaker is Professor Chris Jackson from Imperial College London. Chris will speak about when salt disappears, what are salt beds, and why should we care about them. So if you want to know why should you care about it, so come next week and attend Chris' talk. So thank you, Andrew, once more. I would like to ask all the audience, please stay happy, healthy, and tuned, and we see you next week. Have a nice day. Bye-bye.